Welcome all of you. In the previous lectures, we have derived some important relations between current I and current density J. Okay, J is the vector quantity. We should denote it with J bar. Okay, so I equal to integral J bar dot ds bar. Like that, we have derived so many relations. We have also derived what is continuity equation. Continuity equation is del dot J bar is equal to. See, we have seen I equal to integral J bar dot ds bar. We have also derived continuity equation, that is del dot J bar is equal to minus dou rho v by dou t, and like this. Similarly, we have derived 2 or 3 more relations. After all those derivations, we have seen what is meant by a conductor. A conductor is nothing but it is a material which will allow the free flow of current through it. That means electrons can flow freely through the conductor. There will be many number of free electrons which are available in the conductor. Okay. So based on that fact, we have seen what is meant by a conductor and what is the resistance of a conductor also in the previous sessions we have derived. After that, we are coming to a new concept called as relaxation time. Before going to this relaxation times, we need to know some basic definitions. Suppose, what is meant by a homogeneous system? Homogeneous material. Homogeneous material means if the physical properties of the medium do not vary if the physical properties of the medium do not vary from point to point, then such a system is called as homogeneous system. Okay, that means you are taking one medium. That medium may be some air or liquid or gas, something. When we can say that medium is homogeneous means if the physical properties of the medium do not vary with from point to point. If the physical properties of the medium does not vary from point to point in a medium, then that such a medium is called as homogeneous medium. Okay. Suppose everywhere you can observe in a homogeneous material, at every point the physical properties will be same. Suppose you are taking one conductor. If you consider at this point or this point or this point or anywhere, at every point in that material or in that medium, the physical properties will be same, constant everywhere. Such a system is called as homogeneous system. Suppose if the physical properties go on varying from point to point, if the physical properties vary from point to point, then such medium is called as non-homogeneous. Okay. If the physical properties of the medium does not vary from point to point, and if at every point their physical properties remain same, constant, then such medium is called as homogeneous medium. Suppose if the physical properties go on varying from point to point, then such system is called as non-homogeneous medium. Okay. So after this we should also define what is meant by a linear system and non-linear system. Suppose if you are taking a medium, in a linear medium, d bar and e bar should be directly proportional. If d bar increases, e bar should increase, and if d bar decreases, e bar should decrease. This is electric flux density and this is electric field intensity. D is electric flux density, E is electric field intensity. Suppose if both these quantities are proportional to each other, then such medium is called as linear medium. Suppose if they are not proportional to each other, if d bar and e bar are not proportional, if d bar and e bar are not proportional, then they are called as non-linear mediums. Non-linear medium. Okay. So we have seen what is meant by a homogeneous medium, non-homogeneous medium, linear medium, and non-linear medium. That medium may be anything. It may be a conductor or dielectric or anything. Okay. Now, if you come to relaxation time in a conductor, suppose now we are seeing the properties of conductors. Still we did not enter into dielectrics. We are seeing only about conductor. In the previous sessions, we have derived the relations between I and J bar in a conductor, continuity equation in a conductor. Like that, still we are progressing in conductors topic only. After this, we will proceed to dielectrics. Okay. Now, consider a linear homogeneous conductor. Already we have defined what is meant by a linear medium and homogeneous medium. Linear medium means d bar and e bar, electric flux density and electric field intensity should be proportional to each other. And homogeneous medium means in that medium at any point the physical properties or physical characteristics of that medium should be constant. Physical properties will not vary from point to point. Such system is homogeneous system. So we are assuming a linear homogeneous conductor, and for that conductor already we have derived the point form of Ohm's law. What is the point form of Ohm's law? Point form of Ohm's law is valid for conductors, which we have derived in our previous class. So point form of Ohm's law is J bar equal to sigma E bar, where J bar is the current density, E bar is the electric field intensity, sigma is the conductivity of that conductor. Okay, and we are also having the relation D bar equal to epsilon naught into E bar. Okay, we already know this relation from our first unit. D bar is equal to epsilon naught into E bar. So from this, what is E bar? That is D bar by epsilon naught. Now you substitute this E bar in this first equation. Substitute this second equation in the first equation. After substituting, what you will get? J bar is equal to sigma into J bar is equal to sigma into what is E bar? D bar by epsilon naught. Okay, so J bar is equal to sigma by epsilon naught into D bar. Okay, suppose if you are taking the free space, then epsilon naught value is fixed 8.85 into 10 power minus 12. Suppose if you are considering a good medium, here we are taking a good conductor. A conductor like copper or aluminum will have its own relative permittivity. So instead of epsilon naught, we should take epsilon here. Suppose we are taking a free space, then epsilon r value is equal to 1. So then we can take epsilon naught directly. But what is epsilon? Epsilon is epsilon naught into epsilon r. Here, for any conducting material like copper or aluminum, we will have both epsilon naught as well as epsilon r. So in this place we should substitute epsilon. So if you substitute epsilon, here you will get E bar equal to D bar by epsilon, and in the place of J bar equal to sigma E bar, I am substituting. So we are having point form of Ohm's law, J bar equal to sigma E bar. So in the place of E bar, what I am substituting? D bar by epsilon. So that is sigma by epsilon into D bar. Keep this relation aside. Now for a conductor, we have also derived continuity equation in our previous session. So if you see that continuity equation for a conductor, what is the formula? Del dot J bar is equal to minus dou rho v by dou t. Del dot J bar equal to minus dou rho v by dou t. Del dot J bar equal to minus dou rho v by dou t. So in the place of J bar, this J bar, what you can substitute now? J bar is sigma by epsilon into D bar. Del dot J bar is sigma by epsilon into D bar. This question is very important because In your last year EMF paper, they gave this question directly. Derive the relaxation time for a conductor. So please concentrate on this. So del dot sigma by epsilon d bar, because in the place of j bar I am substituting this value. So that is equal to minus dou rho v by dou t. Now how can we improve this equation furtherly? This equation can be furtherly improved as, bring this constant outside. Sigma is conductivity in number and epsilon is permittivity in number. This is constant. So bring that constant outside. Sigma by epsilon into del dot d bar. Sigma by epsilon into del dot d bar is equal to minus dou rho v by dou t. Okay, but from the Gauss law Maxwell's first equation. What is the Gauss law Maxwell's first equation? We know that del dot d bar is equal to rho v. Already we have derived this in first unit from Gauss law Maxwell's equation. While explaining about divergence, we have derived this expression. Del dot d bar equal to volume charge density rho v. So in the place of del dot d bar, what we can write now? Rho v. Sigma by epsilon into rho v is equal to minus dou rho v by dou t. So this is one equation. Now keep this and we should solve this first order differential equation. So all these derivation is valid for linear homogeneous conductor. So what is the final equation? Sigma by epsilon rho v is equal to minus dou rho v by dou t. So I am bringing this to the left hand side. Dou rho v by dou t plus sigma by epsilon rho v. So this is the first order differential equation. Now on solving this in our mathematical procedures in M1, now what is rho v? Rho v equal to some constant rho naught into e power minus sigma by epsilon into t. Okay, this is the solution for volume charge density rho v. That is the quantity here we should find, variable quantity. So rho v equal to, after solving that first order differential equation, generally we will get in this format. I think you know these derivations in our mathematics. So after solving by that, we will get rho v equal to rho naught into e power minus sigma by epsilon into t. Okay. So from this we can also write rho v equal to rho naught into e power minus t by tau, where tau equal to, if I am changing that, I am representing t by tau actually. Okay, generally you are having sigma by epsilon. So generally you are having sigma by epsilon in upside. But if you are representing it as some tau by something, means that tau is equal to reverse of this quantity, that is sigma by epsilon. Okay, actually you are having sigma by epsilon, but by tau if you are doing means epsilon by sigma seconds. So just how to solve this means, just general procedure of solving the first order differential equation with variable quantity as rho v. So rho v equal to rho naught into e power minus sigma by epsilon t. I am representing it as t by tau, where tau is equal to reverse of this quantity, epsilon by sigma. So this tau is called as relaxation time. This tau is called as relaxation time. Okay. Now how can we define relaxation time? Means it is the time taken by the charge density. It is the time taken by the charge density to decay to 36.8%. So this tau relaxation time is the time taken by the charge density to decay to 36.8%. So 36.8% of its initial value. Okay. So once again I am revising. So you have got this first order differential equation. I am adjusting like this, dou rho v by dou t plus sigma by epsilon into rho v. So here the variable quantity is rho v. So after finding the solution of this first order differential equation, we will get rho v equal to rho naught into e power minus sigma by epsilon t. I am comparing and writing minus t by tau. So I am comparing this, tau will become reverse of this quantity, that is epsilon by sigma. So this tau is called as relaxation time. Now how we can define the relaxation time of a conductor means it is the time taken by the charge density, to decay to 36.8% of its initial value. A time taken by the charge density to decay to 36.8% of its initial value. So this is the concept of relaxation time for a conductor. Okay, so based on this we should do some problems. Anyway, first we will move to dielectrics, and after that on the combination of both conductors and dielectrics we will solve some problems. Okay, so this is about the concept relaxation time of conductors. So until now whatever the derivations and concepts we have seen, those are all related to conductors only. Conductors are the materials which will allow the free flow of electrons or current through them. The number of free electrons available in a conducting material are very high. Just on the application of small voltage or potential, immediately they will start moving and they will constitute the flow of electric current. So these are the important derivations for conductors.